So this talk's going to be a little different. I'm going to tell you a little bit about my career path and what got me here today. I would like to say it was a straightforward line and that I had it planned out from day one, but that's not what happened. The path worked pretty well until I became an adult, and then things changed, you know. But I'm going to try to give you a little idea of what got me here, and some funny stories hopefully, and then some science mixed in there. I'm originally from Ohio, and is Lisa here? Lisa. Lisa thinks New York ends and there's nothing else. So Lisa, I put this map up here for you. So here's, whoops, this is the one. So here's where Ohio is. And I actually grew up in what is called southern Ohio, down here kind of around Cincinnati. And I grew up in a fairly rural area. We did grow up on a farm. We had a lot of cattle, which we milked. We also had pigs, which are extremely mean. I don't recommend it at all. And we also grew crops. And I have to say it was very hard work, and Mother Nature is not forgiving. And so that's one reason why I'm not a farmer. I learned early on that that was not what I wanted to do. Part of what I did learn, though, is that what farming teaches you is that when you have a job to do, you do that job. There's no excuse the tractor doesn't work or something's wrong. You fix it and you move on. And I think that was actually a really good lesson, and has taught me that there's usually always a way to work around things and move forward. Now, the town I grew up in was extremely small. The high school I graduated from, there was only 100 people in my graduating class. And the joke was that there was always more cows and pigs than there were people in that town. And there were some good pluses of it. The negatives was that my parents knew everything I did, usually before I even knew what I was doing. I remember one time when I was in high school, my boyfriend decided to break up with me. My dad found out, drove up, and he got an earful. So anyhow, it was a very interesting experience. Whoops, now I did it. Oh, I have to go backwards. So if you haven't been in part of Ohio, one of the things that it's really known for are these Indian mounds. And there's a number of them that are actually throughout the state. Most of them are actually in the southern part. And this is one of the most famous ones called Serpent Mound. Have any of you ever heard of Serpent Mound? Many times you'll actually see it in your history books, and they talk about the mounds that were in Ohio. And it's actually a serpent. It's about 1,400 feet long, and at the mouth is actually an egg. And it's a park that you can go, and you can actually go and learn about this. This is actually in what's called Adams County, and this is where my family is originally from. And actually my great-grandparents were the original caretakers of this property. And so I have a rich history outside in beautiful country, which I appreciate very much today. So if you ever get the opportunity, you should attempt to go see this. Now, as I said, I went to Blanchester High School. It was a very small school. There was about 100 people that was in my graduating class. And I can't say that when I was in Blanchester that I was thinking I'm going to be at Brookhaven National Lab someday. That really didn't happen. Originally, I thought when I was thinking about my career path that I wanted to be a veterinarian. I love animals. I love taking care of them, and I thought, that's what I was going to do. And then one day while I was volunteering at a veterinarian, someone had a dog, and they had abused that dog. And my reaction was not what you need to do if you're going to be taking care of people's dogs. So I realized at that point that veterinarian was probably not going to be my calling. So then I had to decide what I was going to do. And in my family, my uncles and my grandfather were engineers, so they're like, Cathy, you should become an engineer. And I was like, well, I don't have any other ideas, so let's try that. And so when I was looking around for places to go, I went to school. I went looking at different colleges, and I had gotten offers to go to small colleges. And after my small town experience, I decided I'd had enough of that, and I wanted to go to the city. So I looked at Columbus and Cincinnati, and I decided on going to Cincinnati. And part of the reason I decided on Cincinnati is they had a very good engineering school, and at that time they had a co-op program. And I'm someone who likes to get her hands dirty, and so I thought I could go there, do engineering, and get my hands dirty and get some experience, and I'd be set by the time I get done. That was part of my plan, which turned out not to work out. So I went to the University of Cincinnati. I started out in engineering, and the engineering school was a very good engineering school. And the challenge I had is that they had so many students coming in that they really didn't care about the students. So it was a challenge for me being in a class where I had a teacher who really didn't care about the topic that I was learning. And I really cared. I was there, I wanted to learn. That's why I was at school. So I started looking around at other things that I could do. And so my grandmother, who had a huge impact on my life, was an artist. And she used to do painting, and so I thought, maybe I'll try ceramics for a while. So I was still taking my classes, but I went and started doing some ceramics. And I was doing that, and then I thought, you know what, I'm gonna try to get a job. And so I was still doing classes, and there was this ad came out for working in a toxicology lab. And I thought, this will be great. You can learn how to work on animals, and we were going to assess compounds in humans. I thought, this will be great. So I signed up for this job, and it turned out to be an incredible job. But there were certain things about it that were a little challenging when you're 18 years old. So it turned out I didn't know what the research topic was, and the research topic was evaluating chemicals on the male reproductive system. And so there were 3 parts to this huge grant that this guy had. So one part was we would expose these male rats to compounds. Then we'd have to go and the male rats would get to go and have as much sex as they wanted. And someone had to go in and figure out how much sex they had. And that was my job. And it was intriguing. So part of what I had to figure out was you have to actually observe which ones are good at sex and which ones are not, which takes a little while. And they tend to like to do this in the dark, which is another challenge, especially if they get away from you. But that was one part. The other part was it turned out that part of the study was we were looking at workers who worked in the sewer system and were exposed to chemicals at a random basis and what the impact was. And so we had questionnaires which we asked them, which when you're 18, asking people about their sex life was a little challenging. But what was more intriguing is when they show up and give you their semen sample that you then had to go off and analyze. So it was actually a really good project, and I learned a lot. And one of the big things I learned from that was really how to do a lot of animal work. So I really learned how to evaluate compounds and do studies. So after that, I was doing my ceramics and thinking I was going to, become an artist. And I started realizing that I was not asking the right questions that the artists were asking, and that I was far more interested in how to make the glazes and the pottery work than I was in making the art. And I mean, I made some good pieces. I had some shows. People bought my pieces, but I realized I was going to starve to death if I pursued that path. And so then one day I was sitting in a chemistry class, and this professor got up and he was talking about chemistry, which was not something that I'd ever thought I was going to do. Basically because most of what I saw in chemistry just didn't seem all that interesting. And this chemistry professor got up and he started talking about inorganic chemistry. And he was showing how he could make these compounds, and they could more or less use these for doing imaging on the molecular level of in vivo function. And he was showing some images that they had done of him, of different things, and I was just fascinated. I mean, after the talk, I went up and started talking to him. And I said, hey, can I work in your lab? And he said, sure. And that was it. That started my career. And it worked out really well because it turned out his animal person had a bike accident. And so since I knew how to do animal work, I could do my research there. So that was kind of like the start of how I got into doing chemistry. So I actually got my bachelor's in biochemistry and then went on to work in inorganic chemistry. And I started doing my research actually on the bachelor level. So These are some of the compounds that we work on. So if you don't know what a chemist does in this, if you're an inorganic chemist, it means that you take radio metals and you build compounds around them. And the point of these compounds is it gives them the characteristics that determines where they're going to go in vivo. So these are some of the compounds I looked at, and I'll give you some idea of the different properties that we actually changed. Many of these are fairly famous compounds that are currently used. These are actually used for brain imaging. And this is a compound that was used, that is still used, I believe, in kidney imaging and also for labeling peptides. So I started out on technetium. So technetium should be very familiar to you here at Brookhaven because the technetium generator. It has ideal properties for imaging and is used in 85% of all radiopharmaceuticals that are used for imaging. So one of the first projects I started on was looking at brain imaging. So this is a scan, and this is something called TEC HMPAO. And this is a scan of a patient who's undergoing a seizure, and you can see, or a stroke, I'm sorry, and you can see the low blood flow in this part of the brain. So what this agent allows you to do is to look at abnormalities where there are differences in blood flow and determine the location of where it occurs. Now there's some problems with this agent, and part of it was no one was really quite sure how it worked. So when I first thought, there was some hypothesis. What we know about the blood-brain barrier is that for things to cross, they have to be neutral, lipophilic, and fairly small. But what wasn't really clear is why it was getting trapped. And so part of what my goal was to try to see if we could come up with a better agent and to see if we could more or less keep it trapped. So here is more or less the structure of the HMPAO. And one of the problems with this is that it's very unstable. So when you formulate this compound, you have to use it within a few hours' time, or you can't use it anymore. And when I was at the University of Missouri, we had a hospital, and what they were interested in was an agent that you could do the formulation, and you could have it sitting on the floor, so that if a patient, like if a child was undergoing an epileptic seizure, you can do an injection and immediately image them. So part of our goal was to try to increase the stability of this. So our first attempt at this was to add this bridge at the top. And so that bridge would make it more or less structured and try to more or less increase the stability. The other thing we were interested in is trying to vary the lipophilicity. So we knew the lipophilicity was important, but we weren't sure how important it was. So we designed these compounds in which we added an oxygen here to try to increase the stability, but then we added these groups, these methyl, ethyl, and propyl groups, to more or less try to vary the lipophilicity and then look at how this affected the overall brain uptake in vivo to see if we could overall improve this compound. And these are our studies that we initially did in normal rats. And these are the compounds in which we varied the lipophilicity. And the lipophilicity varies as we go across here. And so we took different time points and we measured the uptake. And so what you can see is that the uptake varies by lipophilicity, that one with the most highest lipophilicity has the highest uptake. What we also unfortunately observed is that it's really decreasing with time. And so although it causes you to have an initial high uptake, it doesn't really stay there. And this just kind of shows you the results, showing that indeed the lipophilicity follows out of the brain extraction, with the highest lipophilicity having the highest extraction and so forth down. So the next thing we wanted to look at was the stability and see how the stability affected it. So this is the agent that was approved, and here you can see how fast this compound decomposes, which was part of the challenge with using it. Here's the cross-bridge version we originally came up with, and you can see we've improved the stability. And then here are the ones with the oxygen, so this really improved the stability. So now the question was, how is this going to impact the uptake? And so here more or less we see what the impact of the stability was with the oxygen giving us the highest stability, followed by the cross bridge, and then by the HMPAO. When we looked at the uptake, this is the uptake in vivo. And so this white line is the original HMPAO. The red line is the CBPAO. And then these are our oxygen derivatives. So we can see that the oxygen ones cleared out pretty quickly and they didn't stay. But we can see that the two that are unstable actually stay for a fair amount of time. We then went on to look at something called the blood-brain ratio. And what this does is it tells you how much is actually extracted versus what's actually in the blood. And what you want to see is a very high number here. And so what you see if you look here at our, the one with the cross bridge, it has very high uptake actually in the brain. And so this was a marked improvement over that observed for the HMPAO. So we actually went on to take this into clinical trials, and we had very good results and in this actually in patients. So from these studies, what we learned was a little bit about the impact of the lipophilicity and the stability. And so we saw that the lipophilicity aided in getting that initial extraction, but realistically, if you want to have it stay in, you've got to do something to actually trap these agents in the brain, either instability or something where it actually complexes to more or less to keep it. Otherwise, it just crosses back out. After that, I went on to look at bone agents. And so technetium bone agents are commonly used for imaging, particularly patients who have metastatic disease. So often when you're diagnosed with cancer, one of the first things they'll do is actually give you a technetium bone scan. And the original agents were designed on looking at what they called inorganic phosphonates, which is a POP bond, and they would bind the technetium to this. And these phosphates have high affinity for the bone. The problem gets to be is that there are enzymes that cleave this oxygen, and so these compounds would fall apart and end up not being attracted to the bone. So then we kind of modified this by putting in this carbon atom. So by replacing this oxygen with the carbon, it made it resistant to the enzymatic cleavage, and therefore you would have higher uptake. Additionally, by putting this carbon in, we now had something that we could add substituents to, which we could further modify the uptake. So what we were interested in is really looking to see if we could treat the pain associated with this bone cancer. So we wanted to look at agents with rhenium-186. So rhenium is a radiometal that has properties that are very similar to that of technetium, but it gives off an electron which you can actually use for therapy. So the reason we're interested is that about 70% of advanced cancers actually will end up being metastasized to the bone. And the problem with these is that they're extremely painful. And this pain is so debilitating that these patients end up having to take large amounts of medicine to actually deal with the pain. And so the way they used to deal with this is they would give you opiates and narcotics. And these things lose their effectiveness with time, so what you have to keep doing is increasing the amounts that they're giving you, and then they start becoming toxic, and the patients kind of lose awareness of what's going on. So what they really wanted was a better method that they could use actually to treat this. So they could try to relieve this pain and improve their quality of life. So the two first agents that were used was actually something called phosphorus-32 orthophosphate. And this was comparable to that POP bond that I showed you, and it would be taken up at the bone site. One of the problems with this is that it has high uptake in the bone marrow, so you ended up having a lot of hematopoietic depression, so like your blood cells and so forth. Another agent that was used is strontium chloride, or strontium-89. And in this case, you had the same problems. So these elements ended up going to other places besides the disease site, causing problems. So there was a lot of interest in looking at developing other ones that would be more selective. So going back to the technetium compounds, we wanted to look at some ligands for rhenium. So this is the compound that's typically used for the technetium that's used for imaging. And so we did some studies in which we kind of modified this, and I'm just showing you 3 derivatives here. I think we actually had 10 that we came up with. And we evaluated the uptake of these agents. Actually, it turns out a young rat model is the best model to use for this. And what we discovered is that these 2 versions were actually the best. And they were the best because they showed high uptake in the tumor and kind of low uptake in the bone. So these agents actually went on, this went into clinical trials and actually was approved in Europe for treating this. It was never actually approved in the US, but it actually did very well in patients. Now the other thing we're interested in is at the same time there were other groups really looking at developing these radionuclides for treating this bone pain. There was a group actually in Missouri that was looking at a samarium organic compound for doing it. We were looking at the rhenium compounds, and then many of you have heard of Suresh here from Brookhaven. He was actually looking at a 10 version, 10117M organic compound. And part of the question got to be was which ones of these are better and why? And no one had ever done any comparison. So I wanted to compare these to see really if we could come up with any idea of which one might be better and what was going on. At the point when we were doing this work, there wasn't a lot of understanding of what goes on with the mechanism. So what actually happens to these things when they actually go to the bone surface. So we were trying to evaluate more or less how much of this is taking up in normal bone, because that is toxic. And so what we'd really like is an agent that goes to the site selectively and washes off the normal bone. So what I was looking at is the uptake of these on normal bones, what happens to them and what form comes out. So when we looked at these, we took these compounds. I had a lot of rats. I hope God's not a rat. And I did these long studies for usually a couple months at a time, in which I would inject these compounds, and then I got to collect the urine and the feces and extract the compounds to see what the compounds were, so I could get an idea of what was really going on. And so what we found out was that the rhenium compounds, rhenium wants to oxidize up to perrhenate, and perrhenate is ReO4-, and so it's not selectively retained in vivo. So these compounds would oxidize up pretty quickly and wash out of the bone. The strontium and the tin had some similar properties, and then what would happen is that in vivo at the pH given, which is about pH 7 at the bone surface, these would form hydroxides, and they would tend to stay in the bone and kind of circulate around, which became a problem. For technetium, it has less of a tendency to oxidize, so more of it stayed on the surface. This isn't really a problem for technetium because it's an imaging agent and it goes away. For therapy, which the agents stay there for a long time, becomes more of a problem. And then for the samarium, what we saw is it basically stayed on there and didn't come off at all. So if you look at these, you would say that the rhenium was actually optimal because it had the lower uptake on the bone surface when you use this to compare this model. We actually, as I said, did this in patients, and one of my other lovely jobs was I got to collect patient urine and extract these compounds, and more or less showed that what we observed in rats actually worked in humans. And that's what actually helped advance the trials in Europe, so I'm glad that my work helped patients. What we further learned from this was actually the mechanism. So there was basically 2 mechanisms that were proposed. One was that the compound, so your radiomiddle bound to the compound, would go to the bone surface, and more or less the distribution afterward would be dependent on this compound. The other mechanism was that the compound stayed intact, went to the bone surface, but then the radiomiddle became separated from the chelate, and then what happens to this radiomiddle is actually dependent on the chemical properties of that radiomiddle. And that's what I observed in my study, so that more or less implied that this was the mechanism that was occurring. So based on that, I actually got a PhD and graduated, which was a nice thing. I then stayed on here, and actually, because I said we had clinical trials going on with this bone agent and with the brain agent, and so I stayed to help get us through those clinical trials. After that, I then had to kind of make a decision about what I was going to do. And they actually wanted me to stay at the University of Missouri to carry on their radiopharm program. But at the time, I didn't really feel like they had the support or the money. And I thought it would be a mistake for me to stay on there under those circumstances. So I started looking around. And I got some offers from the East Coast, but it's kind of expensive out here. And as postdocs, they don't pay you that much. So it was going to be really difficult for me to survive. So I got an offer from Washington University in St. Louis, still in the Midwest, Lisa, you see right here. And basically it was with a guy called Mike Welch. And Mike Welch actually did a postdoc here with Al Wolf many years ago. He did hot atom chemistry. He then went to Washington University to set up the program there. And he's probably one of the best radiochemistry people in our time, I would guess. And so it was going to be an incredible opportunity to go work with him. And Washington University at that time was number 3 in the country at their medical school. So it seemed like a good place to go. So I went to Washington University, and what they were interested at the time is developing positron emitters. So they wanted to develop radiometals to more or less do imaging. And the ones that they wanted me to focus on was really copper, and they wanted me to focus on the gallium-68 generator. So that's kind of some of the work I'm going to talk to you about today. So so for the gallium-68, as many of you may know, I tried to tie some of this stuff back to BNL. So you guys actually make germanium-68, or we make germanium-68 here, which is the parent for the gallium-68 generator. And so there's been a lot of interest in this for a while for trying to develop a generator for doing positron emission tomography. And at the time that I went to Washington University, there was really no agents that had been approved, but there was a lot of interest, so I was given the responsibility of trying to come up with some agents that could be used in the clinic. So in looking through the literature, I actually found this compound. And this is a compound that was designed by Stephen Koch. And Stephen Koch is actually at Stony Brook University. And what he was interested in doing is he tries to formulate compounds that bind to iron. And he's trying to understand how iron behaves in enzymes. So he wants compounds that kind of lightly bind the iron, and the iron can go back and forth between iron 3 and iron 2. So he designed this compound, and this really didn't work for him because it turned out that this compound really held the iron in. So it didn't allow him to do the type of studies that he wanted to do. However, when I looked at this compound, what I realized is that gallium is very similar to iron 3+. They have the same ionic radii, ionization potential. So what this means is that the chemistry between these two is very, very close. And so what I thought is that this compound was small, it was neutral, it was lipophilic, and it might actually bind the gallium stably, and this would give us a gallium agent that we could use for possibly imaging the brain and the heart. So my first studies were designed at trying to do the chelation of this. And if you think life is hard, you should take something that's 68 minutes, try to do chemistry, inject it into animals, do the biodistribution, and try to do metabolism studies. It tends to be a very long day. So these were some of our initial studies that we did, and these are actually in normal rats in which we injected the compounds, and we wanted to more or less evaluate what the uptake looked like. So here you see the gallium-68 brain uptake. So this was the first gallium agent that actually showed uptake in the brain. So this was like phenomenal. And when we looked at it, it showed distribution very similar to copper PTSM, which is a perfusion agent. We also compared it to carbon-11 ethanol, which I've misspelled, which was different. So this gave us some idea of the properties of this compound. So then we wanted to see, well, it's nice in rats, but can we more or less use it in something closer to humans? So we did some studies actually in baboons, and this is a baboon. And this is a PET CT, or an MRI PET study. And so we did the imaging, and we saw uptake in the brain. The other thing that was interesting is it turns out baboons have very high uptake in their snout. not clear why. But based on these results, we actually got a patent for this and pursued this actually further into patients. And this was actually a study that was done in a dog. So you're going to see that I did a lot of work in dogs. Mostly these are dog patients. They're not dogs that we're going to sacrifice. This was in a dog, and we wanted to see if we could see the heart. So dogs are a very good model. They very much mimic what we see in humans. So we imaged this dog, and here you can see when we do the initial injection, and you see the uptake in the heart, the lungs. Here you see the lungs, and here you can actually, with time, it clears out of the lungs, and you see a very clear image of the heart. So this was actually a very good, so we had an agent that imaged the brain and the heart. So then I moved on to copper. And so we wanted to look at using a small cyclotron for making copper isotopes. And there was some initial work that was done with this, but we thought what we could do is use some electroplating. And this is, you know, it's kind of funny, you throw these slides up here, and it looks like very simple work, but this takes months of people's time to get all this worked out. So it took us quite a bit of time to get it worked out that we could actually get the electroplating down, get the chemistry done, and get the copper made. And using this, we were actually able to make copper 64, copper 60, and copper 61, which we then went on to evaluate. So why are we interested in copper? So one of the things we were interested in was trying to use this to image hypoxia. And the reason we're interested in hypoxia is that it turns out that, for instance, if you have a heart attack, one of the things we want to know is if the tissue is lacking oxygen, but it's still viable, so it's not necrotic. So we can actually use this to image that and say, okay, we can still save this tissue. The other reason we're interested is that when people have tumors, many of the drugs that have been developed to treat these tumors require that oxygen is there. So if oxygen's not there, that drug's not going to work. So we want an agent so we can see if the tumor is hypoxic, so we know, so it can inform the therapeutic decision. So this was a compound, and this was originally designed by a guy in Japan, and he developed this copper ATSM. And so I contacted him and said, hey, you know, we would like to look at this and see if they can do this. So he actually came to Washington University for about a 6-month sabbatical. And we took our copper and we labeled this compound. And it turns out when you label this compound, that if you put it in tissues that are hypoxic, that are lacking oxygen, it reduces this copper to copper 1 and the copper comes out. And then the copper becomes trapped in that hypoxic tissue, so it allows you to image it. If it's in normal cells with oxygen, the copper stays in, the copper basically washes out. So it gives you the ability, as you can see here, it has high uptake in hypoxic versus normal tissue, so it gives you an idea if you can actually image that. So this was one of the first studies we did to actually look at this compound. So we went back to our rats again, and we took the rats and we actually did some suturing to cause an occlusion in that model. So we put in a suture in there to cause some tissue to be hypoxic. We waited 10 minutes. We actually injected our copper 64 ATSM, about 50 microcuries. Then 9 minutes later, we injected the carbon 11 acetate. And the acetate basically measures the viability of the heart tissue. So it gives you an idea that the heart tissue is fine. And then what we could do is we could image the carbon 11 acetate first. It would decay away, and then we could image the copper 64. So this gave us the ability to image viable heart tissue versus hypoxic heart tissue. And so these are the results of our studies. So these are actually slices of the heart, shown here. And these are the images that we did with the carbon 11 acetate. And so here you can see more or less the viable heart tissue here. And then with the carbon or the copper ATSM shown here, what we can see is the image of the hypoxic tissue. And you can see that it doesn't correlate with that of the acetate. So these studies actually turned out really well. And so based on this, we actually took this into humans. And so we had a number of protocols that were developed to look at this in a variety of tumors that were suspected. It was never, it hadn't been shown before if they were hypoxic or not. And so one of the first trials were done was actually evaluating women who had cervical cancer. And so what you would do is you would inject the ATSM and you would take a PET image. Then you would calculate something called an SUV, and the SUV basically gives you a factor of how much actually goes into the site. And what we were able to do is to categorize these patients. And what we found is that if they had very high uptake, they weren't responding to the therapy. So this gave us a way to basically strategize the patients and determine that they shouldn't be given this drug and they should be switched over to another drug. So this turned out to be very positive. So shortly after that, I got an offer from the University of Missouri. And I could have stayed at Washington University. And it was a hard decision, so I got an offer to go to the research reactor. And I'd actually worked with the people at the research reactor before. They had actually made the rhenium for me, and I had done some studies with them. And at the time that they contacted me, they were having some issues. They didn't have enough money. It wasn't clear if they were going to keep going. They wanted someone to come in and try to grow the program. And it looked like a big risk in some ways. But I decided, where there's big risk, there's good opportunity. So I decided to try that. I also have a number of kids. And St. Louis isn't always the best place for kids, especially when I was used to growing up out in the country. And so we took them basically back, and we ended up buying about 10 acres and starting to grow things. And I have a huge affinity for animals, as I said. So one of the things we like to grow is goats. I should say I and the kids. My husband hates it. He tolerates it, and that's about it. But here's what some of our baby goats that we have. What my husband does like is fishing, and so this is him. He basically built this big pond, which I was not happy about, basically because our dogs go out there and swim and then try to come back into the house, which is not too good. But anyhow, this turned out to be good for them, so we moved back to Columbia, Missouri, back to a more rural area. So when I moved back there, I got a little bit more interested because they had a research reactor and looking at some of the radiometals that they could develop and use them for doing therapy, which I was really interested in. So one of the ones they've been looking at for a long time was gold 198 and gold 199. They were interested in these because they give off electrons which you can actually use beta particles for doing therapy. But you can also image these, which was shown to be very important. The problem with gold is that gold, kind of like copper, has in vivo reduction that can occur. And you may remember they used to make gold compounds for treating arthritis, and some of the challenges that they had, especially in smokers, is that the gold would come out, bind to other compounds, and you would have toxicity issues. So it's very difficult to actually bind the gold. And we were actually doing some experiments trying to label this with some phosphorus compounds. And what we ended up doing was making nanoparticles. And they were very stable, and so we thought, let's try this. So sometimes you have a mistake and you kind of go with it. So based on this, we actually kind of more or less made a library of compounds that we looked at. So some of the initial ones we made, we had huge problems with the stability and also with the solubility. So we used a lot of what they called green chemistry to design these gold nanoparticles with various sizes and various properties that we could use to more or less inject into tumors. And so one of the first ones, the ones I'm going to show you today, is something called a gold compound which we made with something called gum arabic. And we chose gum arabic. It's a solubilizer. It's in a lot of your cosmetics. It's in the Coke that you drink. It's FDA approved. So we thought if this worked, we could actually get this approved through the FDA pretty readily. So our initial plan is that we wanted to use this to look at prostate cancer. And we thought that one of the advantages of this is that if we size this correctly, that instead of having to inject seeds, you could just do 1 or 2 injections of the gold nanoparticles, and that would be easier on the patients. And our hypothesis was that if we sized them correctly, they would clear from the normal tissues and they would stay in the tumor tissue. So here, in this case, we took mice, we took these mice and we actually put in human prostate cancer cells, and then we injected our gold nanoparticles. And so here you can see, here's our treated group here, and then here's our control group in which we just injected saline. And so what we saw was that the tumors actually, in the group that treated, those tumors died off. We evaluated these further and we didn't see any toxicity, and it appeared to work really well, especially compared to the control group in which it kept going. So based on these results, we decided we wanted to evaluate this further. Now at the University of Missouri, they have a veterinary oncology hospital. And so these are animals that people bring in that need to be treated. And it turns out that dogs get prostate cancer that's very similar to what we see in humans. It basically mimics the way it functions, the way it spreads, and all of that. But there's actually no treatment for prostate cancer in dogs. But we've done other trials in dogs, and what we find is that using these spontaneous occurring cancers, it gives us a better idea of how things are going to occur in humans. So we basically got a grant, and the grant basically covered the cost of this, and we would give the dogs standard treatment after this. So what we did is we did some initial injections actually into some normal prostates, and we found clearance. And then we went on to look at these dogs that had prostate cancer. And so what we do is we would more or less perform a CT scan. We would then put needles, which we would more or less inject directly into the tumors. And then we would follow them with time. And what we saw is in doing this treatment, we were actually able to cure about 10% of these dogs. And we saw massive reductions in their tumors, and we were also able to treat their lymph nodes. When we originally started this, we tried to do a second arm of the study in which we used seeds that are commonly used for prostate cancer. And the dogs actually couldn't tolerate that, so we had to stop that part of the treatment. But based on this, we've gotten patents, and they're pushing forward at looking at this actually in humans. And these are actually, of course, I did this work with lots of other people. These are two of my collaborators, and I love this picture because you're actually looking down into the reactor at the University of Missouri. And that blue color is just pretty incredible. So it was really nice to work with these people. So after that, about this time, they were starting to come out with these targeted therapy approaches. And in these target approaches, what they're really interested in is people starting to realize that these tumor cells have these receptors on the surface that are at much higher concentrations than in normal cells. So if we can target these receptors, it allows us to image these tumors so we can more or less detect disease, particularly if it's spread throughout the body, so that's one thing. It also allows us to quantitate this expression, and that becomes important because if it's high enough, that means we can actually treat it the same way by attaching a radionuclide. So there was a lot of interest in going into imaging and actually treating these. And they're more or less looking at a variety of different things. The most prevalent that was looked at is really the beta emitters, and that's just due to the availability. So these are more or less produced mostly at reactors, and they're highly available. There's interest in alpha particle emitters, but the availability is very low. But one of the things we're hoping to do here at B&L is to increase this, and I'll show you why at the end. And then there are people looking at Auger electron emitters, and I say this because many of you know Suresh, who looked at the tin, which was an Auger electron emitter. So a compound that one of the first ones that was kind of out of the gate is this peptide, and this is called a somatostatin peptide. And so there are patients that get something called neuroendocrine cancer. And when they get this neuroendocrine cancer, by the time they get diagnosed, it's pretty much spread throughout their body. And there's really not very good methods for treating it. So they originally designed these peptides hoping that they could give them huge amounts of this peptide and it would slow down the disease. And it turned out that that was not the case. So there was this guy, Helmut Mecke, who was in Switzerland, and he started thinking that you could use radioactivity to treat these. And he started attaching these chelators to the surface and then trying to treat them with yttrium-90. And yttrium-90 is a radionuclide that's often used for therapy. And at the time when this therapy was started, everyone thought yttrium-90 was it. That's all you were going to need. You could just use yttrium-90 and everyone was going to be treated, and that was it. And one of the things he needed to do was to do imaging of these. And so one of the things that started happening was they were using something called indium-111, attaching it to these peptides and doing imaging. And what they were finding is that they were getting very different results depending on what they were using. And that the imaging, here's the indium-111 down here, and then if you look at the yttrium-90, here it is up here. And so the problem was that the indium-11 wasn't really giving you a very good idea of what was going on in vivo. So they wanted to start looking at some of these gallium agents because it was more closely mimicking what they were seeing actually with the yttrium. The other problem got to be is that what they were finding is that this yttrium-90 has this huge beta particle, and they were starting to see some toxicity issues with this yttrium. So there was some interest in actually looking at other radiometals. Here's some of the pictures of the gallium. This is a typical of what you see for these patients. And you can see that it's a pretty debilitating disease by the time they're diagnosed. So I started looking at radiolanthanides. I had this big reactor which I could make things in. And I looked at the lanthanides, and for those of you who aren't chemists, you remember that periodic table, and there's like these two rows at the bottom. One of them are actinides and one are lanthanides. And the lanthanides are the one at the top. And you almost never talk about them because chemically they're just not very interesting. They're all +3 cations, which from a drug formulation point is actually great because that means if I can design something to bind one, I found something that binds them all. From a nuclear perspective, they have varying nuclear properties, which means varying half-lives and varying beta energies. And this means that I can somewhat pick and choose which one of these I want to use as I get into patients. And what we were finding is that as we get into patients that they're different tumor sizes and tumor loads, it would require this. And they also have large cross-sections, so you can produce these in pretty high quantities. So here are some of the lanthanides, and this is yttrium-90 shown on the bottom. So here's the half-life, and the half-life is important because some of these molecules clear really quick and some clear really slow. So some of these peptides and antibodies can take up to 4 days before they reach there. So if you use something with a really short half-life, you're not going to get much dose there. So you need to match these half-lives. And then these beta energies become important because you somewhat need to match them up to tumor size and also toxicity issues. And to give you an idea of that, this is kind of a visual. So at the top is shown yttrium-90. And what that beta energy tells you is kind of how far that particle is going to travel, and mostly damage occurs at the end of the path length of that beta particle. So you can see for yttrium-90, it travels pretty far. And so what you can see is even when it's delivered to a site, you're going to get a lot of normal tissue toxicity with this. So one of the things we wanted to look at was if we could develop something that had shorter beta particles that could possibly minimize the toxicity. And so the one that we kind of settled on for that application was lutetium. But we also looked at holmium because it was actually very similar to yttrium-90. And one of the advantages of holmium is that we can actually image it. So being able to image this gives us an idea of how to do the dosimetry. So here's samarium quadrimet. I talked to you about this before, and this was used for bone pain, palliation. Here you can see the TEC MDP. You see the uptake here. And here you see that samarium has very similar uptake. Samarium was chosen in this case because it has a large cross-section, it has a short half-life, and it has a beta particle that is pretty ideal for treating this. Now, one of the applications, this was actually one of our first patients, actually, I should say. We did our initial studies in these dogs. We actually saved that this dog was actually cured, and we stopped following her after about 5 years. But it really showed how we could transfer this to humans. I like dog patients. So one of the things we wanted to look at was something called skeletal targeted radiotherapy. So there are patients who get multiple myeloma, And one of the final ways that you can use to treat this is to actually ablate the bone marrow. And the original way that they would do this is they would take the patients into the hospital, quarantine them, and then start giving them huge amounts of chemotherapeutic drugs. And the ideal is to try to ablate the bone marrow before you actually ablate the patient. And it's very toxic and the patients get very ill. And so we thought if we used an isotope with a long-range beta that we could actually use that to target the bone and ablate the bone marrow and possibly give these patients a higher chance. So we actually formulated this, took it through phase 3 clinical trials, and actually saw that we were able to cure 34% of these patients. These trials were very challenging because we had to initially do an image. So we would send the drug off, do an image, and then based on that image, they would decide what to give the patient. These patients were getting 1 to 4 curies of activity, and so that's why the imaging dose was so important. We, in order to support these trials, had to make 500 curie batches of this drug. So it was a real challenge to make these and keep it stable and actually support it. But when you see these cure rates, it was definitely worth it. And here you can kind of see some of the images that we actually got with that Homing 166. And this really showed how imaging was really important for allowing us to tailor these doses so we could actually get these rates. So back to this drug. So Helmut Mackey actually had come to me and saying he needed a new radio metal. And so I had suggested that maybe we could make lutetium and he could go for it. So we started producing lutetium and we actually started shipping it overseas so they could do these trials. And here's some of the results that they actually got. So here's a patient, and he has these tumors here. These are actually the gallium images, and this is actually the image from the lutetium. So this patient underwent actually 2 doses of the lutetium. They're only given about 200 millicuries each. This tumor started out at 21.5 centimeters, and at the last image that they took for this, it dropped to about 1.5. And so this was really incredible. And these patients really had no other option. And this drug is actually getting ready to be approved in the US within the next 6 months. And to show you why this is important, and I get a little choked up here because this is a patient. He was one of the first patients that we treated, and he had no other option, and this saved his life. And you know, there are things that we all have to pick priorities. And for me, when patients come up and I know that I've made a difference for them, that's what matters to me. And he contacted me because he found out that I had made the lutetium that he was treated with, kind of told us his story, and this is why I do what I do, is for these people. So after this, there's a hospital you guys may have heard of called Sloan Kettering up the street here. You guys heard of that? Yeah. So they actually developed an antibody called J591, and it's an antibody that targets PSMA. It's a receptor that's overexpressed on prostate cancer. So they were going through some of the same issues. They were looking at yttrium. They were seeing some toxicity. So they contacted us, and we started making lutetium and working with them actually to do these trials. And these were some of the initial results that they saw with the lutetium. So here you see the technetium bone scan. You can see the uptake in these lesions in the soft and the bone tissue. Here's the injection of the lutetium labeled antibody, and you can see the uptake in these lesions in the soft tissue and the bone. This was the first time that they had an agent that actually targeted the bone and the soft tissue. So this was a marked improvement of this agent. Now there have been some further this was my group at University of Missouri. So these are the ones that kind of did a lot of work. Some of the things that are nice about this, part of the reason I show this is many of these are students. And these students were people who showed up. This guy showed up 3 months before school started, showed up at my front door and said, "Cathy, I want to work with you." And he had come through, I used to give tours for high schools. He'd come through one of those tours to the reactor, remembered it, was coming there to get a physics degree, and he wanted to work there. So he came there, he worked for us, he then went off into the Army and is doing things that I don't know about for them. But many of these students more or less came in, got excited, and now have gone on to pursue degrees in the field. So to me, that's very exciting. So then I moved to New York, the big city, the beach, which I never had before. So this was a pretty exciting opportunity. And why did I come here? So I came here because at Brookhaven you have this 200 MeV linear accelerator. And this linear accelerator enables us to make things that we can't really make anywhere else. And so as we were pursuing in these trials, we saw that there was a real need for producing isotopes that we can't make in other places. So some of the things we're interested in is making some rhenium isotopes. I talked to you about rhenium before. It's often made at a reactor, but it's made in such a low specific activity that they can't use it in the clinic. But here you can make it in low specific activity, so interested in that. We're interested in making some scandium isotopes because they're actually more closely mimic some of the radiometals, so we're doing that. And we're interested in doing actinium-225. So this tool is going to allow us to make things that I think are going to really help improve patients. And to give you some examples of that, this is, I talked to you about that antibody that was developed at Memorial Sloan Kettering. They've now developed some smaller molecule PSMA analogs that are actually in the clinic, and they're evaluating them again with lutetium-177. And they're looking at it with gallium-68. And there's one of the isotopes that I had actually worked at Aeronox for a while, and we suggested scandium-44 because it has similar chemistry to lutetium. And we've done some work with a group actually at PSI, and what they found, these are some original, some results that just came out about 2 months ago, in which they did some studies. This is a patient who has prostate cancer. And here they're undergoing a clinical trial with lutetium, and they did imaging with the gallium and the scandium. And what they found is that the scandium was a much closer predictor of the lutetium. The reason why this is important is because this allows them to get that dose more right, and the more that dose that they can give, the better chance that that patient is going to be cured. So if they have to underestimate, that means they have to lower the dose, and that lowers that patient's chance. So that's why we're interested in this. The other reason that we're interested in Brookhaven is because of the actinium-225. So this is a trial that's going on in Germany, and right now they're looking at lutetium PSMA, this small molecule. And this was a patient. What you have to realize is when these patients enter this trial, they have undergone every kind of approved treatment that they can get, and nothing has helped. So they're entering these clinical trials hoping for a miracle. And this patient entered in trying to get this lutetium. This was their initial image. This was actually a gallium image. And what you can see is they underwent 2 treatments with the lutetium, and the disease kept growing. And so this is not a good sign. So they switched this patient over to actinium-225. So actinium-225 is an alpha emitter, and it can actually give a higher dose and in a smaller range, so it kind of minimizes toxicity. So for quite some time, we've known in animal studies that it seems to work pretty well, but there's not been enough to really do clinical trials. So what this trial showed is that this patient received 2 doses of the PSMA, then went on to receive another dose, and then this patient is now cured. So this patient at this stage is now cured of this prostate cancer. So, and just in case you think that it was a one-off, here's another patient. This patient, actually they did a scan. This is a gallium scan. And this patient, you can see all this uptake that's in the skeleton. So they were afraid to treat this patient with lutetium because they thought the lutetium would end up ablating, the toxicity to the skeleton would be too high for this patient. So they decided to switch over to actinium for this patient. So here you see they've received the 3 treatments of the actinium PSMA. You see the really good clearance here. They give them 1 more. And again, this patient is basically cured of cancer. And so this is why I'm here, is to try to do these things and to help these patients go along. So this is kind of why I kind of chose this path, and why I'm now here at Brookhaven. Hopefully we'll have some further stories like this for you in the future. So I want to thank you for coming here and hearing my path, and I would be happy to answer any questions that you have. Thank you. Thank you.
So I have a question.
Okay.
Do you mind going back to the last one?
If I can, I don't know. This one?
Yeah. How can you tell that the C picture there is cured? You know, when you go from one in the middle or on the right, it looks about the same.
So there's two things. One, you can see the black spots, but more importantly, is the PSA values. So it's the drop in the PSA value once it gets to below a certain rate. Yeah. Yeah.
I get it.
Yeah.
So what are the black spots?
So there's normal clearance. I guess I should have mentioned that before. So when you inject these agents, they have to leave the body somehow. And the way these are designed is to actually, you inject it intravenously, and then it clears through the kidneys into the bladder and out. So that's what you're seeing. Yeah.
I wasn't looking at the PSA value.
Yeah. Yeah, but I mean, it's pretty dramatic, the drop that you see as you go across with the
So
treatment.
do you mind going back one more?
I'll try. Let's see here. Okay.
And that was also the PSA.
Yeah. Yes.
I have a possibly very primitive question. In the early slides, you said that you replace the oxygen with carbon and all that, but you know, in my chemistry knowledge, I don't quite know how can you manipulate single atoms in the molecule. How
Yeah.
can you
Well, I mean, you have to synthesize the compound, and that synthesis was not a trivial one. To make that original, the original cross bridge compound is very difficult to make, and it turns out you have to use some toxic compounds to actually make that. So one of the reasons we switched to the oxygen is because it was actually simpler to make. So we could make the oxygen and then add those different lipophilic groups. But it's a pretty complicated synthesis. It's not straightforward. Yeah. It's not like you pick it up, throw it in, voila, we have it. No. Yeah, you have to kind of design it and do the organic synthesis. Inorganic chemistry tends to be a little easier than the organic portion. Yeah. Yes.
Same treatment can be applied to other types of cancer.
Okay, so if you have cancer and the cancer is at one site, usually your best option is for them to go in and surgically remove it. Okay? If that's not the case and it's spread, this is one way you can do it. But there are other radiomiddles that you can actually use. And if you think about it, thyroid cancer is something that for years people have been using iodine-131, and it ablates it and it goes on. So you really, I think what the lesson to be learned is that as we get into patients, we find that these diseases vary, and they even vary by the patient. So that's why the imaging is so important, because the imaging kind of informs us about the disease, but what it also does is it tells us about how that patient handles the drug and how they metabolize it. So there are some people like me, at least I like to say this, it's not probably true, but I say I'm a slow metabolizer. That's my excuse. And there are some people who are really what they call fast metabolizers, and things clear them really quickly. So in order for them to get the dose, you're going to have to change it to match that patient. So part of what you're learning from these images is really how that patient's taking up the drug, how he's clearing the drug, how it's going through his normal tissues, so that you can calculate what the safe amount of that drug is to give them. And if you don't do this, if you don't do the imaging, then what happens is you have to give an average dose to everyone. And when you do that, that means you can be off by as much as 65%. So your chances of reaching these cure rates are pretty minimal. Yes?
You mentioned it was being done in Germany.
Yes.
Is there an accelerator over there?
I think the actinium they actually have a thorium generator, and so they're actually getting the actinium from that thorium generator. Yeah. We've actually shipped them some material from our accelerator as well, but they didn't use it on these patients. Any other questions? Okay, thank you.